All right, everybody. Sorry I can't be here with you today. Recovering from a bad day yesterday. Let's pick up where we ended off at the end of class last time. We were looking at a set of data where we had the average snowfall for every year after 1945. Like 1995 through to 2005, and these data markers are the actual measurements that were made each year, and we did a linear regression using the tools, the trend line tools in Excel. And we got the equation up here of the trend line, and we then spent some time on this page doing some calculations. We had our original data was here, and then we had used the line est command in Excel and got this block of data, this output here, where the first number here is the slope, and we compared that with the equation on the graph and found that they matched. And then this was the y-intercept. We found that that matched what was on the graph as well. And then we started doing our normal things. We started calculating the deviation. I'm going to get this column of deviations of our data points from the trend line. And in order to get those deviations, we had to figure out the y values of the trend line. And we did that by using the equation y equals mx plus b, y equals slope times x value plus intercept. We programmed that in using the slope and intercept that we got from the line est command. And we got all of these values. We subtracted. This deviation is nothing more than the y value of my data minus the y value of the trend line. And then, as we always do, we squared those values, and we raised these numbers to the second power. And then we took the average of those squared deviations to get the variance. And then we took the square root of that to get the RMS deviation of my data. And then we found that we had 16 data points. We counted the number of data points. Degrees of freedom is 2 less than that, 14. We found that that number was here on our output from the line est command. And then we multiplied by our conversion, or our correction factor, to get the inferred population standard deviation, which was this number here, this 2.7157. And we found that that matched the number up here in our line est output, right here in this location. And so some things in this line est output started to become familiar as we did a few calculations along the way, things that we've been doing for a while. And these are not new things in any way, shape, or form. And then we started talking about the fact that this slope number here has an error to it, has an uncertainty to it, because data fluctuates. And so even though this is the best fit line, we know that if we took data again, it would come up with a slightly different slope, and so the slope can vary a little bit. And so we were trying to come up with an expression to calculate the error on the slope. And what I had been trying to convince you of, let's see if I can use my pen here, make it a little easier to write. I'm doing red. The population inferred standard deviation of the slope was going to be equal to the population inferred standard deviation of my data from the trend line, which is what we had already calculated, divided by the population standard deviation of my x values. And I think yesterday or on Monday when we talked, I think I wrote on the board that this was the population inferred standard deviation of the x values, and that is what you would expect it to be, but that's not in fact what it is. And here's the reasoning behind that. The x numbers, this column of x numbers, are what are called my independent variable, which means I chose these numbers myself. I chose to look at these years from 1995 to 2010. I chose to look at these particular years in 1 year steps in order to analyze my data. Since I chose these independently, I'm assuming that this is the only population of information I'm interested in terms of the x values. This is the population of data in terms of the x numbers. And so, and there's no uncertainty in those. So instead of saying that this is a sample of a larger population and I'm going to have to infer something about the standard deviation of the population, that's not the case. This is my entire population of data that I wanted to look at in terms of the x numbers, the years. If I had wanted more years, I could have chosen them, but I didn't. And so instead of a population inferred standard deviation, it's just the actual standard deviation of this data that I've got right here, these x numbers right here. And in order to calculate that, it's really not that bad. The standard deviation of the x values is going to be calculated using the stdev.p command in Excel. That will give me the standard deviation with no correction factor included, right? I don't want to make any kind of a correction factor on the standard deviation of these x numbers because I'm not inferring anything about the population from these numbers. I'm taking this as the population. So let's just calculate what that is. Okay, let's just do this. So let's get the standard deviation of the x values equals stdev.p of this column of x values So there's my standard deviation of my x values. And so my population inferred, let's do this. My population inferred standard deviation of the slope is going to be this number here, the population inferred standard deviation of my data from the trend line. These are the y values and how they deviate from the trend line. Okay, so equals this divided by the population, or the population standard deviation of the x values. So here's the population inferred standard deviation of my slope. Now, there really is no such thing as the population inferred standard deviation of my slope. This is just a step in the process of getting to what really we're after. Because to get the slope, let's go back to our graph. to get the slope, I had to look at all of this data. I had to look at all of these data points. There's no such thing as getting the population inferred standard deviation of one data point. It's always associated with the entire data set. So it's always taking an average. The slope is always a process of taking an average of all of these numbers, these dots. I'm finding the best slope for this entire set of data. And if I'm reducing an entire set of data to one number, that's like taking an average. And so we know that the measurement of the fluctuations of an average is a standard error. And so this is going to equal this population inferred standard deviation of the slope divided by the square root of the degrees of freedom. Now we get this 0.16 number. Let's make this a little bit bigger. 57, 147. It should be matching this number up here, and it's not. N, I'm sorry. I'm not degrees of freedom, square root of n. Here we go, square root of n. Yep, my bad. Okay, now we're matching. Here we go. 1.14728 matches the 1.14728 up here. Okay, so in our output of our line est command, we have here the standard error of the slope is this guy right here. All right, so let's make that marker there. Okay, that's the standard error of the slope. Okay, and now let's put all this information together, and let's do this. Go to the graph. These dots obviously scatter up and down around this trend line. And they scatter randomly. I think we could say that. There's no pattern to the scatter. It's a random scatter. That means we've got a good trend line drawn. The dots should definitely scatter randomly around the trend line, and they do. This pivot point, this is the point that stays stationary even when I change the slope of the line. I'm going to pivot this line through this point. So this point is always going to stay right here as I pivot the line to show the standard error of the slope. But how do I know this is really the pivot point? This is the pivot point for the particular set of data that I have, but it's not, I mean, there's an error in this pivot point as well. There's an error in the position of this pivot point. Look, these data points fluctuate around the line. So it's also true that this pivot point should have a certain amount of fluctuation, a certain amount of uncertainty in the position of this pivot point. And that fluctuation is only going to be vertical. It won't be horizontal because, again, I chose the independent variables are the ones I chose. We assume there's no error in those. All the error is just vertical. It's in my measurements, not in the numbers that I chose. not in the years that I'm taking this data. So there's a vertical uncertainty in the position of this this pivot point, and that would be the standard error in the y values. Okay, because this data point here is an average. It comes from looking at the average x and the average y. So if we're talking about the fluctuation of this point, and this point is a representation of an average, we need the standard error, but it's a standard error associated only with vertical motion, which is in inches. Well, we have that. We have to measure the y variations, the average size of a fluctuation in the y direction here. We calculated that already. So we need to calculate now a standard error, and I'm going to call it the standard error of the pivot, standard error of the pivot point. So that's going to equal this here divided by the square root of my sample size, like we always do. Okay, so there's 0.68. Let's get a few more digits in that. Okay, so my pivot point can fluctuate up and down by 0.6789. But it doesn't happen very often, 0.6789. So now I've got a pivot that is telling me how my a standard error in my pivot, telling me how my pivot point can fluctuate, and I've got an error in my slope. Both of these represent averages, that's why they're standard errors. And what I want to do now is I want to combine these two errors in a way that is going to allow me to make a drawing on the graph. I want to add some lines to my graph that show me these uncertainties, make a picture of these uncertainties. And here's something that you need to realize. Let me draw something on here. Let me just draw another line here, as if this is a representation of okay, there. Notice something here. Close, let's say that this blue line represents a fluctuation in the slope. The fluctuation in the slope, notice that the size of the uncertainty is 0 right here at the pivot point, because both lines, the orange line and the blue line, both go through the pivot point. So there's no uncertainty there. The uncertainty grows as these two lines get further away from the pivot point. The distance away from the pivot point increases, and as that distance away from the pivot point increases, I get more deviation between these two lines. So the deviation, or the error in my slope, a fluctuation in the slope, creates a situation where the further I get from the pivot point, the larger the uncertainty becomes. I hope you can see that here. All right, close to the pivot point, the fluctuations are small. The deviations between these two lines are small. Further away from the pivot point, the fluctuations or the uncertainties get large. And so we need to take that into account in our equation. And we're going to need to take into account the fact that this pivot point itself can fluctuate up and down by a certain amount. All right, so we need to combine those two things. Let me see here. Okay, so here's what we're going to do. Let's go back here. And we know that when we're adding things, adding errors, adding standard errors, we're probably going to add them like Pythagoras. And so that is exactly what we're going to do. All right, so let's do this. Here's SE average. This is going to be the SE of averages. The standard error, the total standard error that we're going to get when we deal with averages. Remember we said that the pivot point is a representation of an average and the slope error is a representation. The slope is a measurement of averages. And so if we're going to get a standard error taking into account all of these average measurements, these standard errors, it'll look something like this. We're going to add like Pythagoras, so we got a square root. We've got the SE pivot, and we know we got to square that, plus delta x times SE slope, both of those squared, right? Where delta x is the distance from the pivot. Delta x equals the actual x value minus x average, right? Delta x is how far away I am from the x average point, right? So here's the equation that we're going to have to program in. We're going to have to calculate this, okay? But I hope you can see this here. Adding like Pythagoras, we have, two SEs. One is a SE of the pivot, one is the SE of the slope. And in the SE of the slope, we have to add in how far away we are from the pivot point, because we know that the size of the error increases the further away we get from the pivot point. So as delta x gets bigger, this error here is going to get bigger. When delta x is 0, or if I'm right at the pivot point, then this doesn't add anything to the error. And the only thing we're going to have is the SE of the pivot. So let's see if we can calculate this, right? So we'll make a header here, SE of the averages, and equals square root, and then I need my SE pivot, it's this, and I need to square it, plus, and now I'm going to open and close a paren, right, and I'm going to move my cursor in here, and then I'm going to make two more. Move my cursor in here. So this is where I'm going to put delta x in here. This is going to be x. Well, where are my x's? Here are my x's. There's an x minus x average. There's x average. I need to make that an absolute cell address. So there's my delta x. Times the standard error of the slope. There's this, and I need to make that an absolute cell address. And then that whole thing I need to square. Okay. So there's the equation. Let's see if I did it right. All right, yep, we get a number here. Let me show you that again. All right, there's, you can freeze and hold the recording so you can see that. All right, And then we're going to copy this down. And notice that I have large SEs, and then they get smaller and smaller and smaller and smaller as I get close to the average X, and then they get big again as I move away. So let's make a header here. Okay. All right. So this is my SE average. This is the amount of fluctuation that I can expect away from the orange line. Okay, the orange line is if the world is perfect and there are no fluctuations. That's the orange line. But because the world is not perfect and things fluctuate, I can expect both a fluctuation in the slope of this orange line and in the position of this pivot point. And by putting both of those together, I can calculate the amount of uncertainty. And this amount of uncertainty depends on what X value I'm working at, right? What year I'm looking at. And so now I want to make some new series on my graph. So I'm going to create trend plus SE1. And I'm going to call this SE1. Right, and I'm going to make this a little smaller. Okay. And I'm going to do exactly what this header says. I'm going to take the Y trend, which is this column of numbers here, and I'm going to add the error, the amount of error that I've calculated here in this column. I'm just going to add those two columns. So I'm going to take my trend value plus my amount of error, and then I'm just going to copy this down, and then I'm going to do this same thing, only I'm now going to subtract. So I'm going to say equals the Y trend minus, because our errors are always plus minus. So we're going to do one column of plus and one column of minus. And now I've got two columns of numbers that I can use to make some more lines on my graph. So let's go back to my graph. And when you see these on here, hopefully it'll all make sense. So let's select data. I want to add a series. I'm going to call this trend plus SE1. Then I'm going to click on the arrow next to the X values button. And I'm going to select the only X values we've got are right here. This column of numbers right here. The year since 1945. And then I'm going to click on the button next to the Y values, and I'm going to come over here and I'm going to choose this column that we just made, the Y trend plus SE1, because that's what I called this data set. There we go. And then I'm going to add another series. I'm going to call it trend minus SE1. And we're going to choose the same X values. And I'm going to choose the other column of Y values. This one right here, Y trend minus SE1. And now I've got these things that I need to format a little bit. I want to turn off the markers. I want to go to marker options and say no markers, and the line here, and then I'm going to go to this, then I'm going to go to line, and I'm going to say I want a solid line. I want it to be the orange color of my trend line, but I want it to be dashed. And then I want to do the same thing on this set of data here. I want to say solid line. Well, first I want to say markers, no markers, line, solid line, and I want it to be dashed. And let's see, something doesn't seem right to me. F21. Oh, I see what I did wrong here. This has to be an absolute cell address. Did not make that an absolute cell address. And then I've got to put that down. There we go. That should be, there we go. There we go. That's better. Okay. So hopefully what you can see now is a picture of what we've been talking about. If this orange trend line fluctuates, you can see if I fluctuate it, it will fluctuate up to this. On the right side, it'll fluctuate up and down between these two dashed lines. And on this lower side, it'll fluctuate between these two dashed lines. And the further we get away from the pivot point, the fluctuations get bigger. And right in here where the fluctuations are the smallest is right at the pivot point. And this distance from the positive dashed line to the negative dashed line is just the SE pivot. That's the uncertainty in the location of the pivot point. And so if I want to analyze some data for year 60 years after 1945, so this is 2005, I can go here and I can say the average amount of snowfall predicted by my model, this trend line is a model, is about 13 inches. And I could say plus or minus this much between the dashed lines with a 68% confidence level if I assume a normal distribution. Okay, and I'd actually have to use a t distribution to do this more precisely, but roughly speaking, I could say plus or minus 68, 70% is my confidence level that the true population number lies somewhere in this range. Okay, and as you can see, if I go out to this point out here, 2010, the fluctuation is bigger. The uncertainty is bigger. And I would have a larger confidence interval to get the same confidence level. To keep at the 70% confidence, I would have to have a bigger confidence interval because the distance between these dashed lines is bigger. If I wanted more like 95% confidence, I'd have to go 2 of these distances of these dashed lines, right? 2 standard errors gives me about 95% confidence. 99% confidence is 3 of those errors, and I get much bigger confidence interval, much larger swing uncertainty. Okay, so here's a picture of the blue dots are my raw data, and my trend line is the best fit line. It's the line that gets the closest that's possible to all of the data points. Here's the equation of that trend line. And then we do some calculations to figure out the fluctuations, the uncertainties. So we figure out the fluctuations, how much these dots fluctuate in the y direction from the trend line. And then we figure out the fluctuation of my data, my x data, from the average x. And the ratio of those two is the uncertainty and the slope. And I can combine both the uncertainty and the slope and the uncertainty in this pivot point and get a standard error that takes into account all the possible fluctuations of both the pivot point and the slope. Okay? Now, let's do this. what we've just done is we've analyzed, we've made a model from our data, and we've analyzed the fluctuation of averages, the fluctuation of average snowfall. And these are the fluctuations that I could expect to see if I took 16 more measurements of the snowfall, okay, since 1945. If I took 16 more measurements of the snowfall, let's say I just put my measuring equipment in some different locations around, let's say this was done in Chicago. And if I put my snow collection equipment in various places around Chicago, I'll get some different numbers. They won't all be exactly the same. And if I were to take 16 measurements of the average snowfall like this over the same period of time, I would expect my results to fall in a similar, to create a similar model within these dashed lines. And I would expect that with about 68 or 70% confidence that another 16 measurements of snowfall would produce results that lie within these dashed lines and are represented best by this solid trend line. That's what we mean by analyzing the average. We're analyzing the average of another 16 measurements. We're doing the experiment again, and we would expect the results to lie somewhere in this region bounded by these dashed lines. I could also ask the question, if I just picked a single measurement of snowfall, another single measurement of snowfall, let's say here at 62, was that 45, 2007. In 2007, if I made another single measurement of average snowfall around Chicago, well, a single measurement in that year could fluctuate more than what these dashed lines would indicate. These dashed lines are showing me how the results would fluctuate if I had 16 measurements taken over this period of time. I would expect results that fall inside these dashed lines. If I wanted to talk about a single measurement, not 16 measurements, the average of 16 measurements, but a single measurement, I should expect there to be a larger fluctuation. A single measurement can fluctuate much more than 16 measurements. And so we need to do a little different calculation. This is the expression for analyzing the amount of error if we're talking about averaging a bunch of measurements. And in this case, we're talking about averaging 16 measurements. So this is always averaging 16 measurements because that's how many are in this data set, averaging 16 measurements. But if I want the standard error, and I'm going to call it total, and this is going to be for a single measurement, it's going to be this result that we just did, the average, plus the average amount of fluctuation for a single measurement, right? This is the population inferred standard deviation of a data point from the trend line. A single data point can fluctuates on average this amount. Population inferred standard deviation, DT, we called it. And I add them like Pythagoras again. Square them, add them, take the square root. But I have to add this number in here, okay? And this is going to include both the fluctuations in the slope and the fluctuations in the pivot point, plus the fact that I can have a bigger fluctuation if I just make a single measurement as opposed to averaging 16 measurements. And so we need to calculate that. So we're going to get SE total. Okay, this is going to equal square root and we're going to take our SE average, we're going to square it, plus our population inferred DT. That has to be an absolute cell address. And then we're going to square that. And we're going to add those two together. Take the square root, add like Pythagoras. And I get this. Now we're going to copy this down. And so now we're going to do just like we did before. We're going to call this SE2. So this is going to be Y trend plus SE2. And this is going to be Y trend minus SE2, right? And this is Y trend is back here. We've already got that data plus SE2. Here we go. And then we're just going to copy that seed formula down. And then we're going to do equals Y trend minus SE2. Copy that down. All right, let's save all this. And now we're going to add this to our graph. We got a couple more series and a couple more lines to do here. Select data. Let's do trend plus SE2. Pick our X values, same X values as always. Okay, it's just this column here. And then the Y values. Now we're going to pick this. We just created this column so we can make a graph of it. This is the SE2 plus the trend. Okay, there are those. And then we're going to add another one, and we're going to call it trend minus SE2. X values are here. Y values are here. Now we got to format these. Format data series. We want to let's see, we want a solid line, but we want it to be, we'll make it a different dash. Okay, we'll make it a little bit different dash. And maybe I'll make it even smaller. There we go, make it that dash. And then we're going to do the same thing with this guy, solid line, make it this dash. And then we're going to turn off the markers. Then we go back and turn these markers off. Okay. Now, these two dashed lines show me the amount of fluctuation for a single measurement. A single measurement could vary from the prediction from this model. I mean, the prediction of the model is this line, this solid orange line. But a single measurement could fluctuate as much as these two dotted lines with 68 or 70% confidence. Okay. 16 measurements, the average of 16 measurements could only fluctuate this much. Remember, averages, if you average a bunch of measurements, you're going to get a better result. If you take only one measurement, the amount of fluctuation or deviation from measurement to measurement can be much larger. But an average of 16 measurements is going to be tighter. And that's what we see here. And so our linear regression gives us three things. It gives us the model, which is the center line. It gives us the degree of fluctuation if we were to take an average of 16 more measurements. And it gives us the degree of fluctuation that we could expect if we were to make just one measurement. How far could it be away from the prediction of the model? And then we can ask, if we make a measurement, if we make one measurement of snowfall, and it ends up way down here, then we could ask, okay, is that statistically significant or not? Okay, and we can start doing all of our analysis. We can start saying, well, let's do this. Let's do this. Let's see. We'll pick one of these here. Here at 2007. Okay, this is 2007. If we measured the snowfall in Chicago in 2007, first of all, what would the model predict? How much snowfall, what average snowfall would we, for the whole year, would we expect? Well, in 2007, we go right back here and we can say in 2007, that's right here, right? Our model predicts 13.64 inches of snowfall, average snowfall, okay? And that's the center of our distribution. If we wanted to do a hypothesis test and see if a particular measurement was odd or not, we would say, let's say we measured 18 inches of snowfall. Well, would that be odd or not? And we just measured it once. We had one measurement, 18 inches of snowfall. Would that be odd or not? Well, in order to do that, we are going to use a t-distribution because we're talking about the fluctuation of averages, and we don't know the population standard deviation, so we have to use a t-distribution. So we'll put some numbers up here. So we got theory. This is what our model says. And we'll just copy the number here, y trend. For 2007, that's here, 13.64. Okay, so there's that. Theory is that. Test statistic was 18. Okay. Degrees of freedom was 14. Right, n minus 2. And let's get a p-value. So I'm going to use a T dot dist dot right tail. Okay. This is going to tell me the amount of area in the right tail. Okay. And let's see, oh, okay. I got to do something here first. Test statistic, I need a t value for my test statistic because I can't, the Excel commands always only work on a t scale for the t commands. And what else do I need to know then? So I also need to know the SE total. I need to know the width of the distribution that I'm talking about. And I'm talking about one measurement, and so I'm going to be using the SE total, so that we just calculated that. The SE total for 2007 is right here. Okay. So equals this much. This is the standard error, so that's the width of my distribution. And to get a t-value, I need to take the distance from the center. The distance from the center is the difference between theory and my test statistic. Okay? So I'm going to take this minus this, and that has to be then divided by the standard error. That's the t-value, and I have a t-value of 1.5. Now I can do this. Let me move this down. Equals t dot dist dot right tail, and now I know that this says x in here, but it really must be a t-value. And degrees of freedom is 14, and we have 7%, 7.5%. Right, so my p-value is 7.5%. So there's a 7.5% chance that I could get an 18-inch snowfall in Chicago in year 2007. Now, I have to decide if that's statistically significant or not. If I had a significance level of 10%, then this would be odd. This would say that there was an odd level of snowfall that year. If I had a 5% significance level, then this would not be odd. This result is more probable than my my significance level. So, you know, here we're going back to all the same kinds of calculations that we've been doing. We've done p-values and significance levels and critical values and confidence levels and confidence intervals. All that stuff still applies. We still use t distributions and Gaussian distributions, and we have the central limit theorem and all the rest of the things that we've learned. All we've done now is we've found a way to take a set of data that is ordered pairs. I have x values and y values that go in pairs. Here, it's the year after 1945 and the average snowfall. And those have to stay together in pairs. And I've graphed them because both pairs are numbers, and that means I can put them on a graph, and then I can use the trend line tools, and I can do some calculations that show me the average deviations of either averages of 16 measurements or a single measurement, and I can take that information and apply it to any year. In this case, I chose 2007, this year right here. If I chose a different year, then my standard error would be different, right? My standard error would be different. I mean, go back here. SE2 changes with the year. Here it's more like 3. I was at a 2.8, 2.87. Here it's more like 3. And so the results I get are going to depend on the SE, and the SE2 changes depending on what year I'm looking at. But once I have these SE values, both the total here, which is for a single measurement, or the average SE here for an average of 16 measurements, then I can do all the standard things that we've been doing for quite some time. All right. Next time we get together, we'll talk more about what the rest of these numbers in here in the line est command output are. And if you look on the portal, you'll find that I put up a template for you, a template that shows you how to use the line est command in Excel. So go look at that, pull that file down, and you'll see what each of these numbers means, because the template tells you, and it also gives you some example problems worked out, and it shows you all these equations that we've been working with in this lecture. So it's a summary of all these things we've been talking about. But go ahead and read that, look at that, and then we'll pick up with that the next time we get together on Friday. Okay? Hope this was helpful, and this is really where everything comes together. All the things that we've been learning kind of come together in this linear regression, and hopefully you're seeing that. Hopefully you're seeing it's not just a bunch of new things to memorize, but it's really just putting together all the pieces that we've been learning all semester. Okay, thanks.